Here's another example. Why don't you try working through this one on your own as well, and then when you're ready to do it with me, press play. So my free body diagram is the same. In this case, I know what my acceleration is. They're telling me this acceleration. It's the acceleration in the x direction, so that's going to help me figure out my net force in the x direction. So here I'm using Newton's second law. I plugged in my acceleration and my mass, and I find that the net force in the x direction is equal to 3 newtons. Okay, well, how can I use that? I'm trying to figure out the force of friction so I'm trying to figure out this value. Well, now I know what the net force is, and the net force is equal to my pulling force minus the drag force minus the force of kinetic friction. So here I've plugged in all the values that I know, and I find that the force of kinetic friction for this problem is equal to 15 newtons. Let's do one last example. We have a man weighing himself, so he's going to stand on a scale to see how much he weighs. And I just want you to think about, what do you think the scale will read when he's in an elevator if the elevator is traveling at a constant speed? Will that scale read the man's actual weight? Will it read something larger than his weight, or will it read something smaller than his weight? Then consider if the elevator is accelerating upwards. Will the scale read something larger than his weight, the same as his weight, or smaller than his weight? Then consider when the elevator is accelerating downwards, what will that scale read? Okay, so press pause, think about this a lot, and then we'll go through it together. Now when he's traveling at a constant speed in the same direction means that his velocity is constant. That means the net force on him has to be equal to 0. He's always going to have gravity pulling down on him, and I'm going to start writing, instead of just the force of gravity, I'm going to just start writing m times g, because the force of gravity pulling down is always equal to m times g. There's also going to be, acting on the man, the normal force pushing up on him. And as we said before, the scale is going to read the normal force. So really what I'm going to compare is the normal force equal to the man's weight, or is the normal force greater than the man's weight, or is the normal force less than the man's weight? Well, when the object is traveling at a constant speed in a straight line, the net force has to be equal to 0. If the net force is equal to 0, then n minus mg has to equal 0. So in this case, the scale will read the actual weight. N will be equal to mg. Remember, mg is his actual weight. The scale will read his actual weight. Let's contrast that with when the elevator is accelerating upwards. The free body diagram is exactly the same. Nothing in this free body diagram shows that the direction the object is moving or the direction the object is accelerating. Nothing here tells me anything about that. However, if the man is accelerating upwards, there has to be a net force pushing him up. There has to be a net force pushing him up. In that case, this number is going to be bigger than this number. That's the only way to have a net force pushing up. So the scale will read a number larger than his weight. Okay? That might seem weird, but really picture yourself in an elevator standing on a scale. As you accelerate upwards, that scale is going to show a number larger than your weight. Finally, when the elevator is accelerating downwards, our free body diagram is the same, but now because we're accelerating downwards, that means there has to be a net force pulling us downwards. And if there's a net force pulling us downwards, this force is going to be bigger than the normal force, which means that the scale will read a weight smaller than the man's actual weight. Okay, so watch through this video a few times and really think about this, and I hope this starts to make sense to you. We're going to go through this more later with actual numbers to show this is true, but I hope that conceptually this idea makes sense to you as we move forward.